Service Row. This is my submission for the cost optimized LLM gateway. The goal of this project is to centralize LLM requests intelligently, route them based on the complexity to save costs, and use semantic caching to bypass LLMs entirely for repeated queries. As you can see for my architecture, I'm switching to architecture.md. This is the architecture we have. The system is built with the FastAPI uses LiteLLM. FastAPI uses LiteLLM for abstraction, Redis Stack for vector caching, and PostgreSQL for telemetry. The entire infrastructure is containerized using Docker. Redis Stack, which is required for vector search, and Postgres database are all up and running on a shared data Docker network. First, I'm switching to the IDE. I'm running the Docker Compose app build command to run the project. Start the all containers. Now you can see the all containers are going to start it and running healthy. Now we are waiting for Postgres. Yeah. Now I'm switching to the config.yaml. A core requirement is that no business logic is hard coded. You can see my three model tiers: high tier, mid tier, and low tier. Utilizing Groq for inference and OpenAI for and Gemini for embedding. Below I have dynamic routing rules based on token length and keywords like synthesize or architect. I also fallback rules defined here to catch rate limits. Open Now I'm switching to the app codes. In the I'm opening the endpoints for. In the code, when I post V1 completions, V1 completions request the comes in first goes through a prompt processor preprocessor that strips white spaces and reduces the new lines to save on the token cost. Then the routing engine evaluates the prompts against the config.yaml rules to select the most cost effective model. This is a schemas.py. This is the schema we followed for the response. This is a DB database. We use the fast API for this. These are the tests, automated tests we are coded. Now I'm running. I will run the automated test. Before doing a live demo, I want to prove the system's resilience. Here I am running my Pytest suite. You can see the pre-processing test pass proving white spaces stripping works. More importantly, the test fallback mechanism passes the test rate limit error from the primary LLM. The LiteLLM orchestra successfully catches this exception, consults the config, and seamlessly retraces the backup model, returning a 200k OK without dropping the user's request. Now I'm clearing my terminal. I'm running another prompt to invoke I will posting a small prompt like tell me short joke, which is Now for the live API, I will send a simple prompt asking for a joke. Because it's short and simple, the router automatically selects the low tier model. You can see catch hit is false. You can see catch hit is false, and it selected the low tier model Groq Llama 3.18b instant. If I send a complex prompt using the keyword synthesize, the router upgrades the request to high tier 70b model. Our system generates a 3072 dimensional vector embedding for this prompt and stores it in Redis. Now I'm running that prompt like synthesize summary of a quantum mechanics. As you can see, it gives the response like quantum mechanics is a fundamental theory in physics that describes the big behavior of matter and energy at the smaller scale, typically on the order of atoms and subatomic particles. The core principles of quantum mechanics can be some and blah blah. A big response, and the model is switched to Groq Llama 3.3 70b versatile, which is high-end model. Catch hit is false, and the cost is 0.00555548 dollars. Now going to test the whether it the catch. Here the catch hits when we try when we run the same prompt again. Now I'm running the same prompt again. If I run that exam same prompt again, the system performs Cosine Similarity search in Redis. It detects a match above 0.95 threshold. As you can see, model use says cache hit is true, and latency dropped to milliseconds, and the cost is essentially 1 0 near to 0. And opening the models.py in the database, every single transaction is asynchronously logged into the PostgreSQL, so we don't slow down the user response. The schema tracks everything: model use, prompt tokens, completion tokens, total tokens, latency, and catch status. Now I'm running the summary endpoint. We can retrieve this data via analytics and endpoint. Hit v1 like analytics summary aggregates all database rows. Here we can see our total cost in US dollars, total request, average latency, and our overall catch rate, hatch hit rate, percentage from the traffic simulation. Now I'm concluding my cost analysis by I will make you in this. To prove the ROI of this system, I ran a simulation of 50 requests. As detailed in my cost analysis report, if we sent all 50 requests directly to a high-tier model, it would have cost significantly more. By using intelligent routing and Redis semantic caching, we reduced the cost dramatically while improving average latency. That concludes the demo of this cost optimized LLM gateway. Thank you. This is my project. Thank you for reviewing it.